Viajar a California, trabajaba en ICAyCC al mismo tiempo que yo estaba en Manchester, y él trabajaba también con mi supervisor, Peter Jonas. Y entonces ha trabajado en varios proyectos en NASA, recibiendo también algunos premios que están listados: el Exceptional Achievement Medal y el Outstanding Public Leadership Medal. Y realmente desde aquella época, de los años 90, principios de los 90, él utiliza teoría, modelos y observaciones para entender y para pronosticar o entender la física realmente de la capa límite. Y ha diseñado una serie de parametrizaciones para los modelos de gran escala sobre turbulencia, que, como ustedes saben, es uno de los temas todavía no resueltos en física, y cuando se relacionan con la capa límite y con las nubes, introducen una bastante incertidumbre que se propaga en los modelos de gran escala, ¿no? Y entonces, obviamente, también en los de escala regional, como los que se usan acá, ¿no? El Warfield más. Entonces, se han implementado esas parametrizaciones. Pero bueno, voy a ha estado, por supuesto, en un número de comisiones dentro de NASA y también a nivel nacional, y tenemos la suerte de que nos haya contactado para venir a conversar, no solo hoy en este seminario, sino también con cualquiera que quiera hablar con él. Él va a estar lunes y martes de la semana que viene, así que me hacen llegar un mail si les interesa la temática y lo que ven en esta presentación, y también para coordinar el rol de nubes en modelos climáticos y en la ciencia del clima realmente, ¿no? Entonces, bienvenido, João. You can start now.
Muchas gracias. ¿Funciona?
Sí.
Okay. Muchas gracias por la posibilidad. Yo no hablo español. Yo soy de Portugal y hablo portuñol, que no es español. Por eso no voy a tentar hacer la presentación en español. La hago en inglés, pero comprendo español más o menos. Y si ustedes tienen cuestiones o clarificaciones, lo pueden hacer en español, y lo puedo intentar comprender y responder en español, en portuñol. All right, so I'll start in English then, and I'll spend the next 45 minutes. So I want to talk about turbulence, clouds, and climate. And those are, as most of you, if not all of you know, big problems to be addressed in the context of not only climate prediction, but weather prediction as well. And I'm sure most of you have seen a figure like this, or more or less like this, right? In which this is from the latest IPCC, but the previous IPCCs showed very similar figures. So you have basically an anomaly temperature relative to a certain period. Then you have sort of the historical period, and then sort of the forecasting period, right? And there's always like a couple of things that are very obvious here. Is that the prediction of the temperature differs between these colors, and each color is sort of a scenario. So it basically represents a certain amount of greenhouse gases in the atmosphere. So it's an attempt to predict how the world and the economies and the geopolitics is going to be in such a way that we kind of know if there's going to be a lot of CO2 and methane or not. And of course, the difference between them in terms of temperature is very large, right? As you would expect. And that's not the stuff I actually do or worry about. So this is not the uncertainty. Well, I worry about it, but not from a professional perspective. But the uncertainty between the different colors is not what I'm here to talk about, but rather I'm here to talk about the uncertainties within the same color. So for example, for this line over here, this is sort of the median of a variety of models, international climate models. But then there's a standard deviation or some level of measure of variability. And while the median may give you 4 degrees warming in 100 years, lower values could be 2.5 or 3, and higher values could be 5 or 6. So there is, even within the same forcing scenario, a lot of variability between the models, right? There's a variety of reasons why that's the case, but one of the most important one is related to clouds. So clouds, as you see, I'll show you one old study. Clouds are absolutely essential for the radiative balance of the planet. By changing the clouds by 1%, you can actually change the radiative balance of the planet by a few watts per square meter. The point I'm going to try to make in the presentation is that these clouds are intimately very connected to the amount of turbulence and the type of turbulence and the type of convection that exists. And that's the sort of what we're going to explore. And this is a nice quote, simple, basic quote from Arakawa, but this is the sort of thing that people, of course, were already very, knowledgeable. They knew what the problems were, and they knew how to characterize that the cloud is not just a cloud, but the interaction with the large scale and the turbulence and the convection and the radiation and the microphysics. Now, I'm going to show you another slide that is not too dissimilar from this one, but is one that usually is not shown that much. This is the type of slide that is shown a lot. Bear in mind, this is just the anomaly for every model. So every model takes the value of temperature minus its sort of climate of the past. But if you actually plot the temperatures of the models, you actually get something kind of different. So this is the same plot from a previous IPCC effort. I think this is probably, the paper is from 2012, so it's the data from 2007. But what you have here, you still have the anomaly, and the blue ones are corresponding to the previous figure, the anomalies. The black are the observed values. This is just the last 100 years. But what you see here is also the real temperature of the models. So you'll have models that will give you a mean global surface temperature of about 15 Celsius, while other models will give you about 12 or 13. Now you can imagine these are very different planets. And this is something that is important to consider as well, that the models don't just diverge in the terms of how much warmer they're going to be compared to what they were. They also diverge from the beginning, how warm or how cold they were. So, intuitively, it's not necessarily the case that the model that is actually fairly cold is going to respond in the same way as a model that is already fairly warm or closer to what we expect. So keep that in mind. I'm not going to explore this very much, but I always feel the need to show people that, between that wonderful agreement that exists here between the models, the actual temperatures can be quite different, and the climates can be quite different. Now, okay, let's go back to weather, to the atmosphere. And so there's about 3 fundamental reasons why, or very basic reasons why we need to represent clouds in weather models and climate models. And one is that we need to predict the precipitation. Is it going to rain tomorrow? Is probably the question that most people ask. Or when is it going to rain? That's the number one question anyone asks about weather. Another reason, which is related to the climate aspect, is the radiation interaction. Clouds interact with shortwave and longwave radiation in very particular and difficult ways. And they play a big role in determining how much energy leaves the planet and how much is absorbed and all that. And in the middle of all that, what we're going to focus is on the vertical transport. So the vertical transport basically kind of somewhat determines the precipitation and the radiation interaction, but is also per se a reason why we should focus on clouds, because clouds, as I'll show you, like in this particular case, this is a typical shallow cumulus clouds that you can see, most of the time outside. There are places where there aren't many shallow cumulus clouds, but in most places in the world there are shallow cumulus clouds. So this is a sort of puffy popcorn clouds, and the clouds actually determine the transport. The fact that like pollutants from the surface go and get sort of detrained or injected into the troposphere comes through these cumulus clouds. So they play that fundamental role as well, and that's what we're going to focus on. So let me start by showing a paper. This is one of the key papers that Suki Manabe, that got the Physics Nobel Prize 2 years ago, authored in climate. He's sort of the father or one of the fathers of climate modeling. And this is just a single column model. So this is not a three-dimensional climate model. This is just a single column model in the vertical. So he's trying to represent all of the physics of the atmosphere to the best of their knowledge in one single vertical column. And the paper is absolutely essential. And there's many things why you should definitely read this paper. It's very clear. But there's two things I wanted to highlight. One was this issue about the vertical transport. So what you have here, just focus on this line and this one. Don't worry too much about the other one. This is pressure, this is temperature. So these are profiles of the model, the climate, in terms of pressure, profiles of temperature. And this is just when the atmosphere is in just radiative equilibrium. So if you only have radiation on your right-hand side of the equation, this is what you get when you get the steady state. And you can see that it's a very sharp, this very warm surface, and then a cold troposphere. And of course, intuitively, you know that there's going to be turbulence, right? There's going to be convection. If your surface is much warmer than the air above, there's going to be movement of air, right, warming the air above. And this is what happens in this line, which is the realistic line. Is Manabe and Wetherald came up with a very, very simple parameterization or representation of convection, both dry and moist. And they show that it is essential to represent convection, even if very simply, to actually get the profile that you need in climate. The other thing to keep in mind is that they imposed clouds. Clouds were not on the equation. They were not variables. And even in weather prediction, even until the 1980s, for example, mid-80s, the ECMWF model, the European weather model, also imposed the clouds. The clouds were there, they just put historical clouds, and the rain would be predicted, but the clouds were fixed. Anyway, for a variety of reasons, of course, the main one is that it's so difficult to represent. So when they do this, so just look at this line over here, which represents low clouds, which are the clouds in the boundary layer. So these are the clouds in the first 2 kilometers above the surface, more or less. And this is the amount of clouds. This is cloud cover, cloudiness. And they impose, so these are different experiments they run, and they impose different amounts of clouds for this part of the layer. And the remarkable thing is that if you look at the equilibrium temperature you get in the planet, so this is the temperature of the climate at the surface. This is the amount of low clouds. And you see how sharp the temperature changes as a function of clouds. It's almost like 1 degree of change by 1% of change. So 1% of change of the amount of clouds existing in the globe on average would imply almost enough energy to counterbalance CO2 or to double the doubling of CO2. And if you look outside, well, not today, but when you have clouds, you look outside, and if the clouds are 65% or 66, it doesn't really matter for weather, right? Nobody cares. Oh, today was 66, but the forecast was 64. Nobody cares, right? But for climate, it's so important. So that's why this is so important. Now, these are more modern models. So this is a nice historical introduction. This is sort of the modern model. So this is Department of Energy in the United States. So the United States has right now 4 climate models. It used to have 3 until 10 years ago. Then there was a National Academy's report saying 3 is too many, and the Department of Energy created a 4th. So now we have 4. And the Department of Energy has invested a lot of money on this, and a lot of personnel. And they develop a model. This is just, the problems that I'll show you here are very common. This model is not particularly better or worse than other models. So these are observations from both, I think, Calypso and CloudSat. For clouds, these are the low clouds, the boundary layer clouds, these are high clouds. You can see the typical stratocumulus clouds off the west coast of continents. You can see a lot of clouds in the Southern Ocean. You can see a lot of low clouds off the east coast. This is usually like low fog in summer or frontal systems in winter. And for high clouds, you see big peaks over land regions where there is tropical convection. And when you compare the model minus the observations, and that's what you have here, it's one of the models, I think the first generation, you can see that they have big problems. But these problems are very common. So they have too little stratocumulus there. They actually have too much Southern Ocean clouds. And they have a lack of high clouds as well. So these are very common problems, and they haven't been they haven't been resolved. And they've existed for decades. Now, when people develop weather models, and this most of you know probably, when you develop weather models or climate models, because the task is so complex, it's so difficult, and requires levels of expertise. I mean, people that understand radiation very well are not the same ones that understand turbulence very well. They could, but it's so complicated that people dedicate their entire lives to study something, and they develop their own codes. And so a lot of these parameterizations, which are just basically parameterization are nothing else than small models, theories that try to represent the statistical effects of, and I'll show you a bit more about that, the statistical effects of what's going on, because basically we have a turbulent fluid with mixed phase physics and radiative transfer. But in the end, you have very modular parameterizations in current models. So often you have something that will do, let's say, the stratocumulus mixing in the clouds in a separate routine, a separate algorithm. And then if you want to do shallow convection, you go to another separate routine algorithm, and so on with all of these different processes. So the goal of our team and of a few teams around the world has been to actually come up with unified approaches to do this. Because if you think about it, in terms of vertical transport, in terms of the turbulence, the different, having, let's say this is Mexico City here, and this is the coast, and this is stratocumulus, and this is shallow convection. All of this mixing, the dry convective boundary layer during the day, stratocumulus, shallow convection, they're all manifestations of the same equations. So it's kind of, it doesn't make a lot of sense to have different modules and doing these different things. It's artificial, and it doesn't help the model. So our goal is to come up with these sort of unified approaches. Now, one slide to explain in a very summarized manner what sort of the mathematics of the problem is the following, right? So we have these nonlinear partial differential equations that we solve for climate or weather models, right? We don't even know if they have an analytic solution, by the way, right? So supposedly they do, right? And we hope for the best. But they do have solutions that we contrast in weather every day with observation. So we know that the solutions are not too far. By the way, even Navier-Stokes alone, it has not been proven that there's an analytic solution. There's a $1 million prize out there for the last 25 years. But if you prove that analytic, that you don't even have to prove what the solution, you don't have to come up with a solution. You just prove that the solution, that there are solutions that blow up in finite time, and you get $1 million. So if you have nothing else to do over the weekend, why not? So, but we can solve them, right? So what we do is that we break them in little pieces in boxes, grid boxes, right? We create a set of algebraic equations instead of the partial differential equations. So we break the world in boxes. Because the computers are not infinite, the boxes have to be fairly large. So 100 by 100 kilometers was a typical climate grid box. They're getting a bit better. For global weather, I would say 10 and 20 is the typical thing, but it doesn't change the story very much, not in the foreseeable future. And you can see there are clouds in there, and clouds are not boxes of 100 by 100 kilometers. They have a lot of structure, right, at all sorts of scales. So from the beginning of people studying turbulence, like Reynolds and Buzinesk, the idea that in the end, what you need to represent is a PDF of properties, not necessarily one single. You don't need to know what's happened to that little parcel of air around that tree to predict the weather in Mexico City. What you need to do is to understand the behavior, the statistical behavior of the turbulent flow, right? So if you assume that the turbulent flow, for example, in a grid box, so the atmosphere in this grid box is described by a PDF, right? The probability density function, a histogram of properties, let's say temperature. Then you can define the value of the temperature as the mean of that PDF plus some perturbation. And if you grab any partial differential equation that we use, let's say a conservation of humidity or temperature, and I put all the sorts and things terms over there, so this applies to basically any fluid dynamics equation and thermodynamics. If you do this Reynolds decomposition, then you do averaging, you end up with an equation that looks like this. So you have a Eulerian tendency of the mean of the value of the temperature here. Then you have the sort of the mean advection of properties. And then you have in atmospheric models this critical component. Ocean is a bit different. You have this vertical divergence of this covariance, which is the covariance between the vertical velocity and, let's say, the temperature. So it's basically a subgrid scale flux. It's basically the flux that happens up and down, right, in the atmosphere that you cannot resolve with your equations. So you have to come up with dynamic equations for the different statistical moments. And so at the core of the turbulence and convection parameterization problem is really how do you determine this covariance. And so before I go into that, let me just say something, put a good word for large eddy simulation models. Large eddy simulation models are fundamental to understand the boundary layer and to understand convection. I'm not sure if at UNAM people, I know you're running regional models and sort of mesoscale models. I don't know if people are running LES models, but LES models are in the end nothing else than just filtered versions of Navier-Stokes, except because you use them in small domains, you can take advantage of computers by having very, very, very high resolution. So in this case, you have 20 by 20 kilometers domain, but then my resolution is 10 by 10 by 10 meters. And when you look at this, these shallow cumulus clouds, they're very realistic, right? If I told you that this is taken from an airplane, except for the fact that the surface is so strangely smooth, you actually could be convinced that these are real clouds. So LES are extremely powerful tools, and I'll show results that involve LES, so I just wanted to put a good word for that. Now let me just spend like a couple of minutes on thermodynamics. So this is the typical evolution of potential temperature when you have a dry convective boundary layer. So I presume that there's a lot of dry convective boundary layers in Mexico City, right? So the sun comes up, penetrates the atmosphere, most of that energy is not absorbed, warms the surface, you start to generate plumes or thermals or updrafts, and they try to basically bring the energy into the boundary layer, right? And this is what happens to the boundary layer in the LES model. Of course, in reality, there's always inhomogeneities that make things a little bit more complicated, right? This is height, this is potential temperature, and this is at different times. So this is, let's say, sunrise, right? And this is after sunrise. And you can see that what happens is that the boundary layer gets warmer, right? So this is one thing, the potential temperature gets higher. The boundary layer gets deeper, right? So it grows through entrainment. But also, it's extremely constant here. So potential temperature is what we call very well mixed, because there's so much mixing, there's so much turbulence that the value is very similar. To describe this problem, if you neglect, so let's say there's not strong horizontal winds, there isn't much water vapor, there's no clouds. If you neglect all that, your first law of thermodynamics can be written exactly just like this. There's a bar missing here. So the behavior, the Eulerian tendency of the mean potential temperature is just a function of this divergence. Now, when I say just, it's sort of a little bit misleading because calculating what this or coming up with the equations, right equations for this is very difficult. And it has been a challenge, so much so that even today, most models, they have a tough time representing the boundary layer top entrainment, but also what we call the counter gradient flux. And this is basically flux of energy that goes against the mean gradient that we will show you can be represented by these plumes, by these mass flux plumes that I'll talk about. But the equations are apparently very simple. Now, when you go to clouds, clouds, of course, bring all sorts of complicated things related not only to relationship with the turbulence, but also the cloud microphysics. But even from the very basic thermodynamics perspective, if you want to solve these equations, you need to, if you want to have equations that look similar to the previous ones, which means don't have additional source and sink terms on your right-hand side and just have this sort of conserved equation. Of course, if you integrate this in the vertical, you realize that then the mean integrated value in the vertical of this is only then a function of how much this flux is at the surface and at the top, right? So that kind of also makes it elegant to construct other types of simple models. But to do that, we have to create what we call moist conserved variables. So these variables are variables like total water, which is vapor plus liquid plus ice if there's ice. And if there's no precipitation, this basic quantity stays constant, right? You just move from water vapor that becomes liquid, and then later liquid that becomes vapor. As long as it doesn't precipitate, it doesn't go away. So if you replace your equations with this liquid water potential temperature and with the total water, then you can still have equations that are not too dissimilar from the dry convective case. However, the problem now comes, and you don't have to worry about the details. I'm just trying to highlight a little bit of some of the basic theoretical challenges. However, while the potential temperature here represents not only it represents the variable that is being mixed and moved around, but it also represents the buoyancy. It also represents the density. It represents how heavy or how light a parcel of air is. And so it tells you what goes up and what goes down. In here, as you get into clouds, then this variable is not there anymore. That's not that anymore. And actually, you have a buoyancy variable that is a function of also the vapor and the liquid. Now, in the previous case, what I said was true if the vapor is very small. Finally, there's a variable that we use and people think a lot about is saturation, so relative humidity, how far you are from being a cloud, right? So, and I always find it a very intuitive and useful variable. This is just the vapor pressure or specific humidity divided by the saturation value, which is just a temperature, function of temperature and humidity. This is just the same thing from LES. These are different sea surface temperatures, and they lead you to different profiles of this liquid water potential temperature. And there are different structures here that you can actually see. So for example, this one over here is going to be a shallow cumulus associated with shallow convection. The base of the cloud is going to be more or less here because it's very well mixed underneath. And then this is the layer where you have the cumulus clouds. This one, for example, is going to be a bit different. The cloud's going to be here, there's going to be cumulus clouds, and then there's going to be a stratocumulus cloud over here. The reason I'm saying this to you is not so that you worry about this, is not an important part of the story, but highlights the fact that if you have looked at this enough, you can see where the clouds are even without any cloud image, but you know where they are. So let's go back to this covariance, right? The story, the core of the matter. So eddy diffusivity is this idea that this vertical subgrid scale flux is just a function of the mean gradient times some sort of diffusivity coefficient. Now, in principle, you have molecular diffusion that will do this not for the mean variable, but for the absolute or instantaneous variable. But from the beginning, actually, even before Reynolds' work, the French, and every time an English person makes a discovery, there's always a French one that did it before. And if you ever noticed that, and the Russians and the Germans are very keen on that too. But a French called Saint-Venant in the 1850s came up with this as well. And actually, the way they formulated the first law of thermodynamics at the time was not the way we think about it. And they assumed that diffusivity could be anything, could be molecular, but could also be turbulent. Right? So later on, Prandtl, Taylor, von Kalman, Kolmogorov put this on much solid ground. But the point here is to say that this diffusivity approach is very good to represent small-scale turbulence. And it plays a great role in sort of neutral and stable boundary layers. Now, by the way, the stable boundary layer problem is far from solved. If you go to extremely stable boundary layers, it's very complicated, and the diffusivity cannot do it. But surface layer, like Mono-Nabokov theory, if you heard or worked with Mono-Nabokov, it's basically eddy diffusivity. Now, for convection, the story comes from another group of people, right? So you have this. And a lot of this is about different groups of people having different ways of looking at problems, right? So you have the turbulence people that I talked to you about. For convection, a lot of the work has been done by oceanographers like Stommel, but also Joanne Simpson, a very famous meteorologist. They came up with these models for convection, by flying across these clouds. They came up with simple models of how these clouds, should behave, and come up with models like these clouds would be like plumes or thermals or updrafts. There's different definitions and names, which I'm using interchangeably, but they are slightly different. And so the original paper for what I'm going to show you is the mass flux theory, is from Henry Stommel. But Joanne Simpson and others developed that, and Arakawa actually developed this to a very nice place, in which he developed an entire theory that he used as a parameterization for the UCLA climate model. UCLA climate model in the late 60s, early 70s was one of the very few climate models that existed in the world. UCLA doesn't do that anymore. But Arakawa did all that work there, and I'll show you the full equations of mass flux. But here is just to highlight the fact that this is ideas of plumes associated. So while the eddy diffusivity is more an idea of, it's phenomenological, but it's assuming that the small scales all behave in some sort of diffusive way. We just need to find out what that diffusion is and how it depends on the turbulence. For the plumes, they actually come up with a almost mechanistic model of how the mixing happens, using these ideas of plumes. Now, about 20 years ago, P.S. Sibes and myself, while we were at ECMWF, we looked at this from both angles and tried to bring things together. And if you actually do the Reynolds decomposition in a grid box, right? So if you go back to this grid box over here, right? So this is the climate model grid box. And if you do both Reynolds decomposition here, but at the same time also divide the grid box in areas that are going up, so there are the plumes, or the updrafts, and areas that are going down, if you do both things at the same time, then you end up with an expression that will tell you that covariance, that vertical flux, is now has three terms. The first term is the amount of turbulence that exists inside these updrafts. So AU is the area of the box that is covered by updrafts. It's between 0 and 1. Another term is about 1 minus AU, the turbulence that exists around this plume. So if you keep thinking about these popcorn clouds, a lot of the mixing happens inside those clouds, but around it, although there is still turbulence, and if you've flown across them, you know that there's still turbulence, but sometimes they're very quiescent as well. So, but anyway, so that's the turbulence around the clouds. And then finally, this term tells you about the interaction between those plumes and the environment around it. So these plumes, as they move up, they transport properties and they mix the properties with the air around. And so you need these three different terms. Now, in the old days, we don't do that anymore. We assume that the area of the updraft was very small, so this term would drop. We forget about the turbulence inside the updraft. And then we assume that this could be represented in an eddy diffusivity manner, because this is small-scale turbulence. And this one can simplify to this, would then be using the mass flux approximation to actually represent that. And if you look at this equation, right, and what we do is that we don't do eddy diffusivity separately from mass flux, we do it all together. So from the beginning, the algorithm and the code and everything is all done together to sort of blend these different turbulence and convection scales. You can see there are basically three unknowns, right? The diffusivity coefficient, this mass flux term, which is nothing else than the momentum that exists in those plumes, or the kinetic energy, and this is the property of the plume. So this is what you need to calculate. What is the temperature inside that plume? What is the vertical velocity? What's the area occupied by the plume? And what is the diffusivity a function of? And so for this, usually there's different approaches. We often relate this to turbulent kinetic energy. I'll be happy to talk about that for a long time. So we can do that, but I'm not going to focus on that. I want to show you why the mass flux ends up being a very sort of appealing approach that allows us to explore, different ways of closing the problem. So if you think about this big grid boxes, right, and you have these plumes, and they cover a certain area, right? Many of them will have an area. So if you integrate over the plume area, if you assume steady state just for simplification, and then you neglect some sources and sinks, we end up with an extraordinarily simple equation, which is the equation that tells you that the gradient of the properties of the plumes, so as the plumes go up, the gradient, or the mean gradient in the box of the properties inside the different plumes, is just a function of the difference between the plumes properties and the mean environment, and this factor over here, which is the entrainment, the lateral entrainment. So don't confuse that with the top entrainment. There's the other one, basically the entrainment of properties inside the boundary layer. This one is basically the entrainment of properties inside those plumes. But this factor basically controls pretty much everything. So if this factor is very large, it means that these plumes encounter a lot of mixing and they just break apart. But if the plumes go up and they encounter almost no mixing, then they can just go far. Then you have a similar equation, a little bit more complex, because you have this sort of buoyancy difference that basically creates the kinetic energy. And this is the equation for the kinetic energy that gives you the WU. And then the updraft area can be calculated in different ways. And we have explored, our team, over the last 10 years or more, have explored an approach that uses multiple plumes. So up to recently, most of these mass flux approaches would be basically using what they call a bulk plume. So they would have a grid box and you have all these plumes and they would replace the properties of all those plumes by just one plume. They say, okay, we're going to build a plume that has the properties of all those plumes. But it doesn't really work very well because the process is very nonlinear. So what we decided to do is to say, well, in our grid box, we're going to assume that you have multiple plumes. We're going to allow them to exist and see what happens to them. So we start them by PDFs of properties in the surface layer, which we kind of know more or less what they should look like. And then let's say if this is some sort of temperature, of course, the plumes that are already warmer from the beginning would have a bigger chance of growing further because they're already sort of wealthy from the beginning, but then they may face more or less problems in life. So we also have a stochastic lateral entrainment that tells you how often these clouds encounter entraining events, so events in which there's a lot of turbulent mixing around them. And some of them won't encounter any and they go very far, and others will just die down very early because they hit very turbulent layers in the atmosphere. The fundamental part of this, there's two important outcomes of this approach, is that one of them is that you can maintain in the same grid box every type of convection. So now you don't have to worry about transitioning from stratocumulus to shallow convection to deep convection. You can have all of that in the same grid box as long as the plumes, some plumes will grow very little, others will go very far. So they could go up to the top of the atmosphere, the troposphere, and become deep convection. The other advantage of this system is that you don't actually have to worry about the total updraft area, because if you define or determine what the area of each one of the individual plumes is, then at every level, the total updraft area, the total area of these plumes is basically the sum of the areas of the plumes. So let me just show you a couple of results in like what we call single column models. So this is just one-dimensional models. And these are just the updraft properties. So this is the area of the box that's occupied by these plumes. This is the vertical velocity of those plumes on average. And this is the liquid water content of the plumes. This is height. And what you can see here is two types of curves. This is LES. So this is those large eddy simulation models that I talked about. It's basically a variance between several of these models. So it gives you an idea of the uncertainty of the models. Both for each one of these, for the three of the variables. The different colors here are different manifestations of this EDMF approach that brings the diffusivity and the mass flux together. And you can see, ignore the blue one because it's not really part of this. But the colors are more or less irrelevant. The important thing is that, of course, the colors fit within the boundaries almost of the LES. So it means that you're actually reproducing the properties. And these are again these puffy popcorn clouds, right? So this kind of convection here, right? So these are shallow cumulus clouds that occur in different places. They're sort of popcorn shapes. That's the way to explain it in the US. But you can ask the question, why is this? Why does this model do well? And of course, there's all sorts of different ways of interpreting that question. One way to interpret that question and illustrate why actually it works relatively well is by doing a cut across this plume. So imagine that domain that I had there. So now imagine that at about a kilometer above the surface, you just do a cut and you collect the values of temperature and humidity at every point. And there's about 1,000 by 1,000 of them, okay? And you build a PDF, a histogram, really, you call it a PDF. And you build a histogram of properties. So this is the temperature minus the mean. This is the water minus the mean. And this is the PDF of the LES. And you can see two things here, right? So one, most of the points are around this very nice looking Gaussian around the mean. And the mean is really the place where there's no convection, right? The mean is this dry area. And then you have this very long tail, this skewed part of the distribution. This is where these plumes are, and this is where most of the action takes place. Most of the mixing takes place there, right? So you have a lot of air moving up and down there. And it turns out that these EDMF plumes actually do this very well, that when you plot the corresponding plumes for, I think this is a period of half an hour, they all populate this skewed part of the distribution. So the reason why this works well is because you are able to reproduce the skewed part of the distribution where most of the action takes place. Now, most of the work we did until a few years ago was all about the boundary layer. So it's dry convective boundary layers, stratocumulus, shallow cumulus. But again, because these are multiple plumes and the entire theory or approach is set up not based on much more than basically giving the plumes whatever energy they need in the beginning and then give them a random model to see how far they go in terms of entrainment. You could actually easily explore this into sort of deeper convection problems. And a perennial problem that models have is to represent convection over land. So the diurnal cycle of convection over tropical land, it's a very, very well-known problem. And probably many of you know this very well. This is a nice paper written by Françoise Guichard almost 20 years ago. This is what she called explicit models. You can replace CRMs by LES. This was 20 years ago. People weren't using yet. There was no computers. The computers were not powerful enough to do LES of deep convection. Now it's perfectly easy to do. But over tropical convection and subtropical as well, let's say during summer, you can have sunrise, and then you start to have this shallow convection, and then you have this congested clouds. And at some stage in the evening, you have a big thunderstorm and a lot of rain, and it gets cooler. Models have a tough time doing this, both weather and climate models, because they tend to often start convection much earlier. They don't seem to be able to hold the energy in the boundary layer very well. As soon as there's sort of instability, they just boom, explode. And this is still true. Not exactly like this, but it's still true in many models, unfortunately. So what we did, we said, okay, so we have these multiple plumes. Let's bring some very simplified cloud microphysics inside these plumes, and then see how it goes, right? Do we have enough convection to create a realistic transition? And so this is the LBA case, the experiment in Brazil about 20 years ago. This is the time evolution of cloud base and cloud top in the mean. This is the time evolution of the cumulative surface precipitation. In red, you have the EDMF. In black, the LES. Actually, with EDMF, because we have the stochastic entrainment, we can actually have an ensemble of plumes and an ensemble of simulations. And so just look at the median value over here. And what you can see is that it's possible to have a realistic transition from PBL to shallow to deep convection, as long as you have these multiple plumes and these very simple rules for what the plumes should do. And you can do this with one single scheme. So this was sort of the first time that it was, anyone showed that you can actually, using only one approach, only one model or theory, you can actually do all of these different types of convection without the need to bring other things into this. Now, let me just show you a couple of 3D models, and then we can have some time for discussion. This is just one example. So these versions of EDMF have been implemented operationally in a variety of global weather prediction models. Implementing something operationally tends to be extremely complicated because it's already difficult to put something in a model and show that it's better compared to some observations. When you put this into a model that does global weather prediction, they're testing this and evaluating it against everything. So it's really, really a challenge. It takes years to actually get this in, and a lot of work by a lot of people. But ECMWF, the National Weather Service in the US, the US Navy, also the French models, latest, I think is Arpege. No, it's not Arpege anymore. But the latest global model has this as well. And this is just one example. This is a paper by Martin Koller from ECMWF. This is the second version of EDMF they've implemented. These are the low clouds, so the boundary layer clouds from the old scheme before the EDMF implementation. These are the low clouds with the new scheme. And when you subtract this one from this one, the other way around, subtract this one from this one, you basically get this nice increase of stratocumulus clouds that the model suffered, and it doesn't seem to suffer anymore. Now, recently, over the last few years, we went a step further in a way. And this is just to simplify a little bit of the story that I've been saying. So this is for the boundary layer, both stable and dry convection. This is for shallow moist convection, for deep moist convection. And traditionally, you would have eddy diffusivity doing the boundary layer in different forms. And you have mass flux doing shallow and deep convection, often separately. And what we've done was to basically move this to sort of a more integrated approach in which we use diffusivity mass flux together to approach all of the mixing. But there's been other things going on, of course, as well. And one of the type of approaches that have been used is sort of higher order closure. So in turbulence closure, if you keep applying Reynolds decomposition and averaging, you keep getting into equations that look like this. So it is actually possible. So instead of coming up with sort of phenomenological models for these covariances using diffusivity concepts or plume concepts, you can actually, on top of the equation that you already have, you do Reynolds decomposition and averaging, you can actually get an Eulerian tendency for the flux itself. The problem is that in turbulence, you always have to specify the higher moments. They always show up on your right hand. This is called the turbulence closure problem, which is, yes, you can come up with an equation for this, but now you have to specify this person or this entity, which is actually much more difficult to specify than those over there. But there's been a successful, in atmospheric science, there's been a successful version of this called CLUB. It's been implemented in the National Center for Atmospheric Research in the NCAR model. And what we've done on a project with NCAR is to actually bring together this higher order closure with the mass flux. So we basically use these equations and we bring naturally the sort of the multiple plumes inside the equations and we solve it all together. So now the higher order closure is doing the diffusivity part, not the diffusivity, the small scale part, and the plumes are doing the sort of large scale plumes. And you can illustrate this. I'm not going to show you one of the results because they just look similar to EDMF anyway. But what I'm going to show you is again the same thing to illustrate sort of somehow an intuitive way of thinking about it. This is again the same sort of popcorn shallow convection clouds. You do a cut on the LES and you create another histogram of the LES joint PDF, something similar. You have the nice Gaussian here and then the extreme skewed part of the distribution. Again, this is still water, this is still temperature. You can see the mass flux discrete plumes populate again the skewed part of the distribution is really nice, but that this high order closure really is unable to leave the Gaussian world. So in principle, these high order closures are supposed to be able to become non-Gaussian, but they very rarely do. So by combining this with this, that's how you get both the small scale Gaussian and the non-Gaussianity out of the box. And this is sort of my last slide, really. Then I have a summary slide, and then I'm open for questions. And then I have another slide to add more questions if necessary. So I have not only open to questions, I also have questions. But this is my last slide with results. So this when we create this merge high order closure with the mass flux multiple plumes, and we run this without deep convection parameterization. So the ones of you that may be familiar with these models, each one of these global atmospheric models, either for climate or for weather, they always have a parameterization for deep convection. And in this case, we don't need that anymore. What we do is that we have this sort of fully unified turbulence and convection approach that basically uses the concepts we developed for turbulence to do the deep convection. And so here there's two types of results. These are for precipitation. That is for the low cloud cover, so the clouds in the boundary layer. These are the observations. This is the old version of the NCAR model, well, the current version of the NCAR model. This is a version that only has a few more levels. So this is the number of levels, 32, and this 58. And this is our version with 58 levels as well. And you can see that our version is actually able to, for low clouds, to get, compared to the observations, I think it's a little bit better, even better than this one. This one, you could see again the problem, right? All of these stratocumulus clouds are off the coast of South America or off the coast of California. You can see that they're there in the observations. They're not there in the NCAR model. They are recovered with 58 levels, and they're actually a little bit less, but more realistic with the new approach. The same thing for convection and for precipitation. They are all slightly different, but it's very difficult to say which one is better. There's correlation coefficients. You can look at the different patterns. But what it shows is that it's possible. So this is the first time really that I think people did this. It's possible to have this sort of unified turbulence and convection approach doing all types of mixing. And in that sense, it was a very satisfying result for us. So this is the summary. So our key goal is really to come up with unified turbulence and convection parameterizations, include cloud macro physics. I'll mention something about microphysics here. The EDMF approach that we developed blends the diffusivity and the mass flux approach, and it's using multiple plumes we can actually represent realistically, dry convection, stratocumulus, shallow convection, deep convection, a lot of cloud transitions. And now we actually have developed this fully unified because it does all of this stuff together. And we've implemented it and it works. And it's a very strong candidate for the next version of the NCAR model for the next round of CMIPs. Now, I didn't talk about cloud microphysics, not because I don't think it's important and fundamental. I didn't talk about it because it's one level more difficult. And without getting into the details of the cloud microphysics, which many of you know very well are very demanding, very challenging, I wanted to highlight one problem, which is that even the coupling of turbulence and convection with cloud microphysics is something we don't really know how to do very well. And what I'm trying to say, I have a slide about this if you want to explore that, but we don't know even what the right temperature equation is. So when you write the first law of thermodynamics or the energy balance equation, the people from the turbulence and convection community will have the equations written with a certain type of variables, like the ones I've shown. The people that do cloud microphysics will have different types of variables. So we don't even agree on what the temperature variable is. So with that, thank you very much again. I have a bunch of questions, not about this, but about climate modeling in general, if you want to debate that. But I'm very open to questions, and I'm here this afternoon, and I'll be here Monday and Tuesday morning as well. Thank you.
Thank you very much. Super interesting and also nostalgic. Many of the figures that you showed from the earliest era. Abrimos para preguntas. Luis.
Hi, João. Thank you very much for your presentation. So you mentioned here in the summary that one of the major challenges is the coupling with cloud microphysics. So from the observational point of view, what do you think that would be the most important variables, cloud microphysics variables that we as a community need to provide you guys as a modelers in order to improve all these things that you are doing? Is there anything that you have on mind that you said, okay, it would be very nice that we could have this type of observational data that could help you to somehow tackle this big challenge?
So I don't have an answer for you that is different from you probably already know. I think what people are observing makes a lot of sense to me, and I don't have any new variables or variables in which we should focus on. I think it's almost I don't want to call it a cultural problem, but these communities come from such different ways of thinking about the problem that we don't agree on what, probably what we need is to have the modelers and the observationalists, both from the cloud microphysics and the turbulence world, come into a room and then close the doors like they do for Pope election, right? I think they close the doors for the popes, right? Don't they? For the cardinals, they do, right? They do, yeah. But they bring food, I hope, I presume. So close the doors and make sure that people in the end come up with what the equation. I mean, let me give you an example. I don't have a good answer for your question. It's a great question. I apologize. I don't have an answer. It died? No. Okay. This is just one example. This is a very, very basic example. So it's not the answer to your question. If you write the equations as a function of most conserved variables, your cloud cover, for example, or your liquid water are just the integral above saturation of your distribution that is associated with a variable. I can show you here, right? This is total water content. This is theta L. This is Claudius Capperon. This represents the PDF of points in a large area simulation model. Anything below is clear sky. Most of the points are clear sky, and then the skewed part of the distribution is inside the clouds. The cloud cover overall in that area is theoretically is nothing else than the integral of this distribution above saturation. And of course, the liquid water is nothing else than the first moment of that distribution, right? That's the way a lot of turbulence people think about this. When you go to even very simple climate cloud parameterizations, very simple. It doesn't involve a lot of species. You can immediately see that it's a completely different world in which very often people have prognostic equations for liquid water and for cloud cover. Just this very simple paradox of do you use this? And cloud microphysics schemes would have prognostic equations for all sorts of different species, right? and very complicated right-hand side terms. And then you can also have bin microphysics, right? And with bin microphysics, you have a much more, or you have now the very simple super droplets approaches that people put everything, make sure that many droplets are represented by a droplet. But there's no agreement. So I don't know, maybe we need a Pope election system, but I don't have anything better to say. Sorry.
Thank
you. Yeah, thank you very much. Can you comment on when you do this approximations with mean that you are doing a better approximation of what was done before, and you try to use this for forecasting? How much computer power are you using, or it gets better or it gets worse? And let me put you my second comment. And I have the impression that all these things get to be so complicated at the end that the only way of doing things is simplifying. In a way,
that's what we're doing.
But simplifying more.
Yeah, so we're simplifying it. I mean, the question is, what's the optimal point of simplification? Right? You have to simplify it to a point, but not below that, right? So you need to get like the 95%, I guess. To your question about how expensive this is. So this higher order closures can be very expensive computationally because club itself has about 12 prognostic variables that it has to carry in memory everywhere in the world. That makes it quite expensive. The ones that we do, what we do is not very expensive. So this one is not more expensive than both of them together. Actually, it's cheaper because you don't have to jump from module to module. And even if you have multiple plumes, if they are steady state, they're not very expensive. It becomes very expensive if each one of those plumes would have, would be carried. If you have to keep them in memory, then that would make it much more convoluted and require many more operations. The computational cost is an interesting thing in climate and weather model because different computers have been evolving, right? And then there's competition for that computer time. And communities different groups have sort of lobbied for different parts of that. And I think the boundary layer people have not been extremely successful in lobbying for their own needs. One example is we know that if we have very good vertical resolution, so if climate models and weather models will have like 100 meters vertical resolution, a lot of the problems, we already have the physics to do things and the entrainment will be much better. But we've been losing for a lot of communities. We've been losing for the data simulation community. To give you an example, the ECMWF, like every weather prediction model, has to run its entire thing in 2 hours. Right? That's the goal. They know they have to do 10-day forecasts in 2 hours because, so let's say they receive everything before 2 o'clock in the morning, all of the data. Then from 2 o'clock in the morning to 4 o'clock in the morning, they have to run the model. And then from 4 to 6, they start disseminating to the weather centers. It's just the same thing everywhere. So you have to carry 10 days. You have to do 10 days in those 2 hours. In the early 90s, the data simulation occupied probably not even 5% of that time. The model was most of the time. Today, the data simulation occupies 90-some% of that time. And the model carries very little. Ensembles as well. Today, you run all sorts of, at ECMWF runs 100 or 50 ensembles. In the early 90s, there were no ensembles. So from the weather prediction perspective, that's the case. From the climate, those are choices they have to make. So when they implemented club in the NCAR model, they had to make a choice that they want to put some of the computer time there. But they kind of regret that a little bit, and DOE regrets it a little bit. And they started going back, partly because of that. Another big movement in the last few years has been to go to very high horizontal resolutions. Global cloud resolving models. There's big intercomparisons and a big push from some people in the community, mostly in Europe, to run global models with 3 kilometers resolution. But to be fair, which it's a healthy thing to do, of course, but to be fair, most of the problems I talk about here you still need to parameterize them because 3 kilometers is not enough. If you want to do stratocumulus well or shallow cumulus or whatever, there's still a challenge. So our approach does not involve, so doing this is less expensive than doing this and much less expensive than doing this.
Any other questions? Okay.
What about the schemes for radiative transfer in this cumulus formation or clouds?
So another very good point. I didn't talk about this at all. As of right now, we're still using the same. So we're still giving the radiation schemes very much the same information than before. However, because we have multiple plumes, we could actually be more sophisticated and actually give different types of information. Historically, weather models and climate models have neglected most of them have neglected the contribution to radiative transfer from the plumes. So the area that the plumes occupy and the amount of water that's in there has often not been given to the radiation scheme, and the radiation doesn't know about that. And the same thing with the microphysics. One big advantage of having a more unified approach is that you can use all the same cloud microphysics. So we haven't changed anything in radiation. We give the radiation scheme the same things. But because we have multiple plumes, we have been trying different things and trying to be a bit more sophisticated. But radiation is extremely expensive. Long wave radiation can be sometimes 50% of all the physics. So people are try to be very economical with that as well.
Okay. Any other questions, Karina?
Hi, thank you for your talk. I was wondering with the eddy diffusivity parts, is the eddy diffusivity a constant or?
No. So eddy diffusivity, and I didn't talk about that. So the idea is that eddy diffusivity should represent the amount and the type of turbulence that exists that sort of determines the small scale mixing. The approach we have often used is to use turbulent kinetic energy, which is half of W prime squared plus V prime squared plus W plus U prime squared. This one would be, I think I have a slide that vaguely mentions that in the beginning. No, here. There's this delay, right? So.
Yeah. ¿Tiene que apuntar para allá para que salga más rápido?
Here. So the idea is to divide this diffusivity into a length scale and the velocity scale. And so the idea is that you come up with a way of representing the size of those turbulent eddies and their velocity or their kinetic energy, and then you can calculate it. So this is usually used, this turbulent kinetic energy. I can send you references. I don't have anything here. I can send you references if you want. But it all starts in the 30s and the 40s. Actually, the turbulent kinetic energy closure, this is something that's not extremely well known, was developed independently, of course, by Pruntel in Germany and Kolmogorov in the Soviet Union during the Second World War. So they didn't communicate a lot, but they did more or less the same thing. And so sort of the origins of turbulent kinetic energy closure, which is something used very commonly in computational fluid dynamics, is on the shoulders of Pruntel and Kolmogorov. So we should be proud of that. But send me an email. I can send you references if you want. Okay.
Thank you very much for a very nice presentation. I was wondering if about how you decide on which scales you're going to be selecting to make your parametrization work. Because I remember Arakawa always told us that you really need to identify a scale, otherwise, this type of parameterization wouldn't work, because you will have everything is blurred in between scales. And the second question is about epsilon, which is your entrainment, lateral entrainment. Is that something that is part of your calculation? I mean, is it going to be given how if clouds disappear or not, as you said before, or actually, I mean, the height of the clouds? Is that, I mean, those are my two questions.
So again, those are very important points and very active areas of research that I didn't. The first one I didn't mention at all, and I should. See if there's a good figure for this or not. Probably not. So the issue about the area, right, and the scale in which this parameterization is operating is a very fundamental issue that's completely unresolved. These parameterizations often don't know the size of the grid box they're operating on, which doesn't make any sense, right? Basically, you give the parameterization of this, but you don't tell the parameterization or the theory, you know, your operating grid box is 2 kilometers or it's 200 kilometers, right? Because it's going to be very different. So that's at the heart. And Arakawa, you know, his last few papers were about this, right? Coming up with people call adaptive parameterization. So ideally, what you need is a set of equations that not only describe the physics, like the ones I've been doing this, but also depend on the grid box size, right? Because if the grid box is like this, then all of this should be not operate. No, you know, everything should go to zero. But if the box is like this, enormous, then you should have something going on. There are papers about this. People have been thinking about this problem for a long time. There hasn't been a lot of theoretical breakthroughs on this. But it's becoming more and more important because people are trying to run these global models with 3 kilometers resolution. And so that becomes even a more important problem there. Because if your model has 3 or 7 kilometers resolution, you already reproduce some of the mesoscale associated with deep convection, but you don't really you can't really reproduce the thermals of deep convection. You still need 100 meters for that. So coming up with parameterizations that are adaptive is a major challenge. Nobody knows. I mean, we have some papers on it, but I don't think nobody knows exactly what the right answer is. Second question, lateral entrainment is absolutely fundamental. And there's different approaches to that, right? So initially, it's like the mixing length problem in eddy diffusivity and turbulence closure. If you've worked in turbulence closure and you read the papers of Mallory Yamada in the 70s and the 80s came up with this, you know, very sort of elegant ways of deriving all sorts of equations to do the turbulence closure. And then in the end, at some stage in the middle of, I don't know, page 7 or something, there is this, oh yeah, but it only works if you choose your right mixing length. Because if your mixing length is, and the mixing length is this sort of intuitive model about what makes the size of the eddies change. And this entrainment problem is the same thing. This lateral entrainment is 1 over the length scale. That's the dimensions. And it's really about, again, how deep these clouds are. In our case, what we do is that we use some of that knowledge to come up with a Poisson distribution. And so we also make it stochastic in a way. So the plumes don't encounter always the same entrainment. Different plumes will encounter different entrainment. And the idea here is to try to represent the fact that there is turbulence in these clear sky regions that's moving around, but it's not everywhere. So you could have plumes that encounter turbulence and plumes don't encounter turbulence. But lateral entrainment is also absolutely fundamental. Without the proper representation of the lateral entrainment, doesn't matter how elegant your math is, you still don't do very well. So yeah, both crucial problem.
And also it would depend on what has happened before
Absolutely.
in the clear air of evaporating
clouds
and so
absolutely.
on.
Of course.
And the lateral entrainment cannot kill the little cloud at some point. So there are lots of issues. Anyway, we are going to have to stop. So we agradecemos de nuevo la presentación. Very, very excellent presentation.
Oh, thank you. Thank you so much. Thank you. Yeah, if you want to meet me, I'll be around, so just let us know. My email is just my last name at jpl.nasa.gov, and I'm sure everybody knows your email, so